In this video, we're going to informally define the limit of a function at a point. Suppose we have some function we're looking at, and some value c we're interested in. And suppose as x gets closer and closer to c, f of x gets closer and closer to some number L. In fact, suppose we can make f of x as close to L as we want by making x close enough to c. Then we say the limit of f of x as x approaches c is L, and our notation is this. The letters LIM for limit, the statement that x is getting closer and closer to c, represented as so, of f of x equals L. So this is an informal definition, but it should be good enough for our purposes. Let's do an example, and before we do that example, let's make two statements. First, it shouldn't matter how x approaches c. The easiest to understand example of what I mean by that is that if c is here, it shouldn't matter which side is approaching C from, whether it's from the left or from the right. Second, and this is just so important, X approaches C, but does not equal C. F of C does not affect the limit as X approaches C. In most interesting examples, F of C isn't even going to exist. Let's return to our previous example now that we have the proper notation for talking about it. We defined this height function. We asked about the velocity after 3 seconds. We tried to approximate it by looking at these average velocities. And finally, we made the observation that this approximation should get better and better as B gets closer and closer to 3. And now we have a proper way of talking about this. We're looking at the limit as B approaches 3 of this average rate of a change. I'm going to take you to a calculator now. What we have here is a TI-84 emulator. I own a TI-84 in this edition, and I uploaded files from the calculator to make this work, so it should all be above board. And we're interested in this average rate of change. I'm going to have to call BX here, just because that's what our calculator always calls its variables. And as X is getting closer and closer to 3, this average rate of change ought to be getting closer and closer to the instantaneous rate of change at 3. So I'm going to go to my table and let's investigate that. What happens as X gets closer and closer to 3? You can't see what's going on because it's rounding, but if you highlight this, you can. So y is changing. It's just the 0.4 is constant. It would be nice if our calculator didn't round quite so much. It's not exactly making this illustration as easy as it could be, but x is getting closer and closer to 3, and y is getting closer and closer to negative 29.4. Until up to the rounding error of this calculator, it equals it. It doesn't actually equal it though. As I say, that is rounding error. But if we now consider this in terms of limits, as our input is getting closer and closer to 3, this expression is getting closer and closer to negative 29.4. That's the limit. I made the observation that it shouldn't matter which direction we approach 3. What if we approach 3 from the negative direction? Well, same thing. Our inputs get closer and closer to negative 29.4. And finally, what happens if we just let it equal 3? I know it kind of looks like we've done that, but this is rounding error. If you highlight this so-called 3, and if you highlight this so-called 3, you can see they're not really 3, they're just close to it. If we actually enter 3, we get a division by 0 error, but that doesn't matter. We've made this observation that when you're taking a limit, what happens at the value itself doesn't matter. The only thing that matters is what happens as we get near that value. And here, as we get nearer and nearer to 3, this gets nearer and nearer to negative 29.4. And that then is the idea of a limit.